This is section 14.2, and we're going to talk about applications of Extrema. We're going to do some word problems. So there's some steps that I've come up, and that's really all the lecture notes, and then we'll work the problems that you'll encounter on homework. We'll work some of those. So the steps are, number one, of course, read the problem carefully. If you need to read through it more than once, do that. Sketch a diagram if possible. If it's something that requires a picture, let's try to draw something. Number three, decide on the variable that you're going to maximize or minimize and express that variable as a function of one other variable. Find the critical points for that function. So take the derivative, set that to equal to 0 and get the critical points, and evaluate for the max and the min. So we're not doing any different calculus than we've been doing. We just have a word problem that we're going to work through. So the problems are right here. Let's go through these. And they have several parts. And when I printed this part, it didn't print all the parts. So we'll go through the parts as we do this. So number one says, of all the numbers whose sum is 62, so there's a lot of combinations that could be that, find the two that have the maximum product. That is, maximize q equals xy, where x plus y is 62. So these would be the final answers, but in the updated version, you do this in steps. So A part says solve x plus y equals 62 for y. So that just means move the x over. You have y equals 62 minus x. Now substitute part A into p equals xy. So instead of y, we now have 62 minus x. It does say to find the domain of p. Well, we're not going to be less than 0, and we're not going to be more than 62 because our numbers have to add up to 62. So we can't be more than 62. So there's our domain. D part is find the derivative and solve that equal to 0. That's finding the critical numbers. So here's our p. P prime would be 62 minus 2x. Then when we set that equal to 0, we end up with x is 31. All right, so that's x. Evaluate p at all solutions. So that means we're going to plug in the original. Remember, here is our original, or if I have it here in a condensed form. So 62 times 31 minus 31 squared is 961. Give the max value of p and the x plus y that give you that value. So if you do p of 0, you get 0. If you do p of 62 equals 0. And then, so you would have evaluated the endpoints like we did in the max min problems, but we found that p of 31 was 961. So that is our max. So your max is 961 when x is 31 and y is 31. If we go back here, you put in the x and y values there, and the product would be here, the 961. So it actually prompts you through each part, and that makes it nice. Let's go to number 2. If the price of charged for a candy bar is p of x cents, then x thousand candy bars will be sold in a city where? And then they've got p of x is 153 minus x over 10. And here are your 5 parts. So we'll go through. So here's our p of x. Find expression for revenue of x thousand candy bars. So we have to multiply by 1000x. Take this expression, which was the price for a candy bar. And so we're going to multiply by 1000x. So 1000x times 153 minus x over 10 times 1000x. And we end up with the revenue of this. This is our revenue function. And then it is saying in A, find an expression for the total revenue All right, we've done that. We can go ahead and do r prime of x is equal to this. Now, the x value that leads to the max revenue. So if we take the derivative, set it equal to 0, we get 765. That does prove to be a max. So that is the x value, and the max revenue in dollars is 585 to 25 if we plug 765 back into our original. So let's see up here. Find the max revenue. They wanted to know what r of x is. That's this. The x value that leads to that is 765, and then the max revenue, when you plug this into r, you get this. So we break it into steps. We're doing the same thing over and over. All right, a rectangular plot of farmland will be bounded on one side by a river and the other 3 sides by a single strand electric fence. With 2,000 meters of wire at your disposal, what's the largest area you can enclose and what are the dimensions? Okay, now we still have parts to do that aren't shown in that printed part that I did. The very first thing I did was draw a picture. So here's my lovely river, and here's the fence. And if I know that I have 2,000 meters to start with, and it's a rectangular area here, opposite sides are going to be equal, so that's x and x, and then I have 2,000 minus 2x. So those are my dimensions. A part, write an expression for the length as a function of x. So that's 2,000 minus 2x. That is the length. We did that already. Find the area of the field as a function of x. So that is length times width. So 2,000 minus 2x times x, and we end up with this as our area function. All right, C part, find dx. So find the derivative of this and find the x value. So the derivative is 2,000 minus 4x. That's the derivative. Set that equal to 0. Solve it, and you get x is 500. So x is 5. So this is 500, and this is 500, and this would end up being 1,000. So C part was find the derivative and then get that x value. D, find the max area. Well, if we plug 500 into our area formula, we will get 500,000. And that's meters squared, and this is meters. So that gets you number 3. We only have 4 questions on this. All right, a fence must be built to enclose a rectangular area of 5,000 feet squared. So in this one, we don't know how much fence we have. We know the area in here. Fencing material costs $2 per foot for the 2 sides facing north and south, and $4 per foot for the other 2 sides. Find the cost of the least expensive fence. So there we go. Now this one, I don't think there's parts, but we're going to do it in parts. All right. So I've let x be the width and y be the length. And if I know that x times y is the area, then y would be area over x. All right? So now I've got x and x, 5,000 over x, 5,000 over x. Those are my dimensions. And we're talking about the cost of the fence, so we need to talk about perimeter. Perimeter is 2 lengths plus 2 widths. So I've got 2 times the 5,000 over x plus 2x. Go ahead and multiply the 2 there. You got 10,000 over x plus 2x. The cost is going to be multiplying the $2 and the $4. All right? And so this said $2 per foot for the 2 facing north and south, the way I've got it drawn. So that's 2, there's my $2, times this, plus $4 times the 2x. So these are the costs on the outside. Then go ahead and multiply, and you get 20,000 over x plus 8x. Now, if I've got to take the derivative, remember we often rewrite things. So I'm going to rewrite this to be 20,000 x to the negative 1 plus 8x. When I take the derivative, I get negative 20,000 x to the negative 2 plus 8. And I'm going to go write it back in the other form. So c prime of x is negative 20,000 over x squared plus 8. Now, I'm going to set that equal to 0. I want to clear this fraction part, so I'm going to multiply every piece by x squared. Those two cancel out. I'm left with 8x squared there. We're still 0 over here, so we have this. So I have 8x squared equals 20,000 because I moved that over there. X squared is 2,500 because I divided the 8 over there. And then I took the square root and I got x is 50. Now, it wants to know, so my x is 50 for that cost. The cost of the least expensive fence, I need to do c of 50. So that's 20,000 over 50 plus 8 times 50 is 800. So that is your final answer. That is the cost of the least expensive fence. The x value that gave us the minimum when we did the derivative equal to 0 was 50. We plugged that into our cost function. That was here. And we got 800, which is your final answer. So only 4 questions, but good work. And I think that'll give you good experience on working application problems with Extrema.